have some practical, okay? I will have some exercise for you, okay? Exercise. That means it's not count for your scores, but it will give you real practice to do, okay? I hope you will enjoy the exercise, and the exercise will be in the format very similar to that of the examinations, okay? So that will be my part for the exercise. You will learn about that. And I don't know why there's a green. No voice. Can hear the voice, okay? Why there's a okay, so it's better now. Uncertainty, okay, first of all, measurement uncertainty, we need to understand the definitions. And when we talk about measurement, okay, what's the meaning of measurement, okay? Measurement is the science of, it's core part of testings, okay? In testings, we do measurements, okay? And when we talk about measurements, we always talk about a term called the measurand, okay? What we are going to measure, okay? Measurand is something that we are going to measure. And when we talk about something like the temperature of my coffee, weight of me, okay? This kind of measurand is not very good. Why? When we talk about, I would like to measure the coffee temperature, is it a good measurand? I don't think so. Why? Because the temperature of the coffee would change from time to time. When it plays onto the desk, it will be cooling down. Okay? So, if you just tell me that you would like to measure the coffee of my the temperature of my coffee, it's a nonsense because you don't know what you're going to measure. Okay? It's not specific enough to give you the true answer. Because every seconds, the value is changing. And so, when we talk about measurement, we have to tell people what we're going to measure. And when we go to talk about what to be measured, it should be very specific. For example, when you talk about the weight of me, I will give you an example on how to set a measurement very specific. Like, for example, weight of me on a particular date, on a particular time, and I also have the breakfast. Okay, at the time when I measured, I already have the breakfast, or I didn't have breakfast. It will be totally different. And I also tell you that before I make my measurement, I take a deep breath. Okay? So, if you're comparing this conditions and also the conditions without specifying any conditions, it's especially this one would be better. Okay, and you will going to measure one particular moment or a very specific conditions of the thing you're going to measure. Okay, so when you try to do your measurement, please think about whether the thing you're going to measure is specific enough. For example, when we try to measure not just on the weight, but also on dimension, okay? Because in many cases, we need to know the area or the size of something. When we do chemical testing, we have to know about the weight we need to know about the density. Okay, when we have this kind of measurement, it's very important we have to control the conditions. For example, the temperature. Okay, when we try to measure something, the dimension, we need to tell very specific what is the temperature when we do the measurement. Okay, not just the environment, but the object you're going to measure. Okay, because if the object, okay, think about in a hot summer, you're taking one object from outdoor coming back to indoor environment, which is air conditioned with well control on the temperature. Even though like this, the object is still very hot comparing to the environment, and so based on the thermal expansion, is not well controlled for what we are going to measure. So when we do measurement, you have to think about what to control. Just like when you go to have a course of method validations, in the course of ISO 725 laboratory management, you would have the courses on, you remember you would have the course of 633. What is that? It's last semesters or this semesters for ISO 725. Last semester. 633, what is that? Anyone know about what is 633? You would have the environmental conditions. Anything it would jeopardize your results, and any environmental factors that would jeopardize your results, you have to control. Okay? And you also have 6.4, which is equipment. Okay? And you shall have your equipment. Okay? For example, 645 is talking about the calibration, the metrological traceability of your equipment. So you need to have something already in place for that kind of things. Okay. So when we do measurement uncertainty, when we do testings, actually all the course materials, okay, you have learned so far for ISO 725, for method validations, all the things is interrelated. Okay, it's interrelated. Okay, so that is what we try to define our measurements. The measurement is set of operation having the objects of determining a values of quantity. Okay, you try to determine the value of a quantity for an object. Okay, and how you do the measurement, how you do the determining the value of quantity is you do a set of operations. You operate the tools, you operate the equipment, try to find out the value of it. Okay? So what we're going to do, what we're going to find is we're going to find true value. And when we try to find true values, over the years, what I have learned so far is that you won't know it. Okay? You will never have the true value because it doesn't exist. Why? Because your measurement is not perfect. Okay, no one is perfect. Okay, in this room or in the world, no one is perfect. So everything when you are using a imperfect measurement systems, you will generate errors. When you generate errors, that means you won't be able to get the true value. Okay? What we're going to do so many years is trying to do a wide guessing. Okay? We only guess the answer, the results is somewhere here. Okay? It's somewhere here. We only do an approximation or estimations of our values of measurement. And because of we are imperfect, our system is imperfect, equipment is imperfect, so it will generate error. And the error cannot be completely eliminated. And we also know about, I think Professor Lee already teach this part about random error, systematic error. Okay? And random error cannot be compensated, but it can be reduced if we try to increase the number of observations. Okay? And you also learn about when you do a number of measurements, you will come up with something like that, or you will be able to get something like that, or okay, that are the four most general things you do. Okay, and what is this? And actually this probability density. Okay, for example, if we have a bell-shaped observation, we measure infinite time, we generate a bell-shaped curve. And the bell-shaped curve tells me that at each end, the probability is less than that of the center. However, if you're going to have a rectangular distribution, it means any points within this range is equal. Okay? So, this kind of distribution, we call that the probability density function. And the measurement uncertainty, in fact, is trying to manipulate this probability density function. Okay? That's why I told you there is a one very powerful tool, we call that the Monte Carlo. And not Carlo, it's Carlo. Okay, Monte Carlo is one tool trying to manipulate the density functions. Okay, I will teach you later. But anyway, you understand that we can do calibrations. Okay, and after we do calibrations, we will know the deviation between the calibrated value, the reference value, and our readings. And so we can do a corrections to our measurement. That is trying to correct the systematic, non-systematic errors. And random errors we can reduce by increased number of observations. Just like that, okay? We can just do these two tools, okay? And so, therefore, in your method validation course, they will tell you how to reduce the random errors is trying to do duplicate. Okay? You do more replicate, you do duplicate, you will have a better chance to reduce the random errors. And how to reduce the systematic errors, you can do calibrations. Okay, when you do calibrations, you will be able to compensate part of the systematic error. We call that non-systematic errors. And so we can correlate this information into this chart. Okay, assuming we try to measure something infinite times. Okay. It will give you a bell-shaped distributions, okay? And in the bell-shape, for the bell-shape, we know about the midpoint is the mean, okay? And this bell shape is coming from we measure nth times. Okay? And if I try to tell you, you go to measure the nth plus 1 time, okay? Then what will you get? You would be able to get a value somewhere very close to this distributions, maybe here. Okay? And this is talking about an individual measurement. Okay? And so, these individual measurements, when we compare such individual measurement with the mean, the difference is the random error. Okay? So, the definition of random error is a particular measurement, the difference between a particular measurements to the mean concluded by infinite time of measurements of the same measurement. Okay, I don't know, but I think it's more or less the same. Okay, if you go back to here, it will tell you the definition should be like this one. Okay, and when we do the measurements, okay, if we have a reference value to this measurement, for example, we try to do the analysis of a certified reference material. Okay, this one is also in your course of mathematics, and so if the two values here, I try to make it more clear. Okay, we have a reference value from the CLM. Okay, so if this is the individual measurement, so the difference between individual measurement and the mean is the random error. However, if we compare the mean from infinite measurement with the reference value, the difference is the systematic error. Okay, so that would be to conclude between different kinds of error and the situation of the data you are picking and their relationship. Okay? And we understand that if we try to do infinite measurements, we will have this bell-shaped distribution, and we understand that the bell-shaped distribution can be like this or can be like this. Which one is better? Usually we talk about this one is better. Okay? Because it's more precise. Okay, precise. Precise or precision is talking about the closeness of agreement among results. Okay, when we have different results, how close they are is talking about precision. Okay, and accuracy is not just talking about among the measurements. Okay, just like if you go back to one slide before, when we talk about random error, we are talking about n measurements, comparing with n plus 1 measurement. And it's just comparing within our measurements only, just like here. So the random error actually is talking about, is related to our precisions. If our measurement is not precise enough, the difference or the random errors should be large. And accuracy is another dimension we try to looking for, whereas accuracy cannot just compare between our measurements. It needs to compare with something external. Okay? Usually the external value is what we call the reference value. Okay? Because we don't have true values. We can only have reference values. So when we talk about accuracy, is the closeness of agreement between a test result of measurement and the acceptable reference value. Okay? Or in bias, it's very similar to that of accuracy. It's talking about systematic difference between results of measurement. Okay? What's the difference between accuracy and bias? If you take a look to the definitions, accuracy is just talking about one particular measurement and the acceptable value. Just like we comparing this one with this one is the accuracy. Okay, a particular measurement and the reference value is the accuracy. Whereas bias is systematic difference between results of measurement and the true value. So the systematic error is actually talking about the bias. Okay? So if you try to correlate between these two slides, it should be like this. Okay? So this is the illustration about how good in precision and accuracy to that. Okay? Think about a blue eyes, okay, like this. We have precise and true and accurate. Okay? Okay? Precise is 精, accuracy is 準. Okay? Okay, so this one is very typical from different textbooks. You will learn about what is precision and accuracy. Okay, and I hope you know these guys from the Olympic Games, but actually it's not the guy, it's not me. And you know about the repeatability, reproducibility, and intermediate precision. What's the difference? Repeatability, talking about measurement under the same conditions. You use the same, you don't need to take photos. You have your notes, I believe. Okay? Unless you want to take photos of me. And so repeatability is talking about measurement under the same conditions. What's the same condition? Same guy, same equipment, same reagents, same environmental conditions, same methods within a short period of time. Okay, that would be the same conditions. So if we do it like this, it would be repeatability. Okay, we call that okay. Well, how to write? Okay, L72. And reproducibility. Which is you go to change a little bit on the conditions. For example, you have your results conducted by one set of equipment, one set of operator A under the environmental condition or something. And if you change a little bit, for example, you change the operator, you try to find another operator to do the same testing again, and you compare the result. That is already changed in conditions, and we call that the reproducibility, and see if you can reproduce the result 重現返同樣嘅 results. Okay, and so that would be reproduce. Okay, the difference between repeatability and reproducibility. This is very important because in different situations where we do our testings, we have to choose whether we do repeatability or reproducibility. Okay? Think about a lab. In a lab setting, I don't know whether you have go to visit some of the very large scale laboratory in the market. When you go to take a look onto the market, let's say for example, I have been working in one of the biggest lab in Hong Kong. And if you go to the laboratory in CHK, you probably will have, in the laboratory, you probably will have one set of GCMS. Okay? So every time you do that by yourself, you go into the lab, you do the GCA analysis, it is a repeatability. Because you have no choice, you only have one set of equipment. However, if I go to a laboratory, got 50 GCMS, and you are going to estimate the measurement uncertainty of the laboratory in the laboratory level, then you have to do not just on repeatability, you have to do reproducibility, because I cannot control to use the same equipment to do the same samples for a particular customer. When I found the result is failed, I want to repeat the test, I probably would change to use another equipment to do the measurement. I cannot control to use the same equipment, the same operator, the same set of reagents or consumables to conduct the test. So I have to do reproducibility. Therefore, when we try designing the estimation of uncertainty, we have to choose the use of reproducibility when we try to design our measurement schemes. And intermediate precision is trying to change the condition, but within the same laboratory. Okay, reproducibility can be changed in laboratory as well. Okay, we can change by testing by different laboratory. Okay. Okay, so one thing I would like to teach before I go into the measurement uncertainty when I take a look to your assignment or in your exam scripts, I found one very typical case is that if you still remember in the consumer product testing course, there's one question asking you guys to calculate the formaldehyde concentration. And I would like to tell you there are around 30 students. I got more than 20 different versions of results. Almost no one is the same. Why? The reasons for that is because you guys have missing one leg in your calculations, okay? Which is very fundamental, and I believe most of you guys have learned that ever since in your lower secondary schools. In your secondary schools, okay, you should learn about two things. Okay, this one is even not in the secondary schools. It's in your primary schools. Okay, anyone don't know what is decimal place? The other is called significant figures. Okay? I can tell from most of your results, okay? Most of the results from that particular questions, okay? I can tell you most of you, around more than 80% of you, do not know how to operate these two tools. Okay, so let me give you how that missing part. Okay, when we do some measurements, we usually can get two types of values. One type is called the exact value. What's the meaning of exact values? How many, for example, how many students in this room? Okay, you can get an exact value. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 10, 11, 12. 32 students, okay, full class. Okay, so no need to take attendance. Okay, no, there's 39 students in this course. 32 students attend. Okay, don't worry, I'm not so careful about the attendance because it's just another estimation of measurement uncertainties. And so, when we do that kind of values, it's usually an exact value. Okay? It's very exact, true value. In this room, there are 32 students. Should be a true value. Okay, nobody can argue about that. Okay, because it's an exact value. On the other hand, we also have some measured value which is not very certain. Okay, for example, if I try to measure a volume like here, okay, you will never get the true answer because it's not. Most of the time, it's not exactly at this line, or even though exactly at this line, it will still be slightly deviating. So, what you can get is just a guess, an estimation of values. You tell me most of the time, okay, when I do chemistry laboratory, people when they operate this kind of measuring cylinder, they would only tell me, okay, from this value, okay, it's now 18 mil. Okay? Then I will tell them that, can you try to divide the divisions into 2 parts? Then you can have 17.5 or 18.0, something like that. Okay? You can do it like this. But even though you do it like this, or you try to subdivide into 5 different segments, you can have 17.2, 7.4, 7.6, 7.8, 18.0. Okay, even though like this, you still not giving me the exact value. Okay, you never can give me the exact value like this. Okay, so we have 2 types of value. Sometimes the exact value is not an integer like the constant, like the pi. Okay, you will learn this number infinitely, but you know this is exact value, but you will never get the correct decimal point because it will be never ending. Okay. So when we try to report something, the key point is that you better try to measure something with the best digit you can have. Okay? For example, if you try to measure it like this, okay, 4.5, okay, 4.5, a little bit more, so you reported 4.55. So instead of you giving me 4.5, you give me 4.55, you will have 1 more decimal point and 1 more significant figures. Okay, that would be better. Okay, and if you try to measure the weight, if you use a balance with only 1 digit, 1 decimal point, or have 4 decimal point, then it will be totally different. So when you try doing measurement, when you try doing your estimations of uncertainty, it's better that you obtain as much as decimal point or significant figures you can have. It's the best practice. Okay? First of all, when you do your measurement. So it's very easy that you go to buy more sophisticated equipment. You try to read more than that. Okay? But one thing I would like to tell in many of the students, do you know what is this? Volumetric flask. If this volumetric flask tells you that this is 25 mil, what would you say? In your lab report, most of the students would tell me that 25 mil of solution A. That's it. Okay? However, the best practice is telling me because the volumetric flask actually can give you 2 more digits. And so that would be totally different if you go ahead on your calculation based on only 2 significant figures or 4 significant figures. Okay, it would be totally different. Another metric is that you need to understand how to determine the significant figures. Okay? For example, there are 4 rules, and all the rules is regarding the 0. Okay? The first rule is if I have a number like 94.072, okay? This kind of number, there's a 0 in here. Okay? I would say 9472 are all digits. And whether the 0 is count or not in here. In this example, if the 0 is in between other non-zero digit, then it is significant. So we got, for this number, it will be 5 significant figures and 3 decimal points. Okay? So you need to have an idea to determine how many decimal points and significance first. Okay, the first step is you need to tell me how many significance and how many decimal points. In this figures, in these values, we got 3 decimal points. Okay? Decimal point. Okay? Significant figures. Okay? This is secondary schools. Okay? You learn this from your secondary schools. Don't tell me you didn't learn it before. Okay? You already have your undergraduate degree. Okay? You have your bachelor degree at least. Okay? So you should have able to learn about that. Second rule is that if it is beginning and before and after this decimal point, then that's 0, okay, like 0.0834. The 0 before the 834 is not count. So in this number, you will have 4 decimal points and 3 significant figures, because this one is not significant. Okay? Okay? Rule number 3. The 0 is at the end, and after decimal point are significant. Just like here, 25 mil and 25.00 mil. This one got 2 significance. This one got 4 significance. This 20 is significant. Okay? So this one, this number 138.200 got 6 significance and 3 decimal points. Rule number 4, if this 0 is before the decimal point, we don't know whether it's significant or not. Okay? Why? For example, 84500. The 00, we don't know whether it's significant or not. Why? I ask you one question. Do you guys know how many money in my pocket? Not much. A few hundreds. Okay? A few hundreds. That means it is, for example, 800. 800 something. When you try to represent it in data format, I will tell you about 800. And this 0, I don't know whether it is exact value or not. Definitely not. And so this one, the digit I can confirm is the 8 only. So I only have 1 significant figure for this case. The 0 beyond the non-zero digit, but before the 00 is unknown. Until I tell you that I got 800, until I tell you I got this. Then I got 4 significance, 1 decimal point. Okay? So these are the rules of 0. And if you know how to do the 0, then you have to learn how to do plus or minus and multiplying and dividing and divisions of numbers. Okay? So based on the last slides, you already know how to determine the number of this decimal point and significance. And so we now go to plus or minus, okay? Primary schools. Okay? Here is one of the examples. If I want to add 318 liter plus 0.01315 liters. In this case, if I put it in this tablet form, then you'll be able to give me the answer. If you're now having a calculator, you will try to tell me the answer is 3.19315. Right? Okay? I can tell in many of you guys' answer in the examinations, many of you try to copy exactly the same of the results from your calculator to the answer. And I tell you now why you are wrong. Because if you try to add the last digit 5 here, but this digit you don't know. Something you don't know at 5, what is that? You don't know. So similarly for this one and similarly for this one. So the only certain digit you can have is here. So in this case, if you try to give me an answer, you can only give me 3.19. And you have to run this uncertain digit. Okay? You have to do the rounding at this digit. So based on the result, this one is 3, so you round it off and you will give me 3.19. Otherwise, if you give me this one is 5, then you will round up and then you will give me 3.20. Okay? So from this example, it tells you that when you do plus or minus, how many digits you have to report is determined by how many decimal points you are certain. And from these two data, one, you only have 2 decimal points. And here you got 5 decimal points. And so the answer, you can only give me the HCF of that. So you can only give me 2 decimal points in the result. And you have to run in the 3rd decimal point. Clear? This situation is for plus or minus. How about multiplying and dividing? When you do multiplying and dividing, like this one, 278 divided by 11.70. Okay? Most of you guys in your answer will give me I really see this answer. in the exam. Like this. Okay? You can give me the most accurate instrument ever in reading of formaldehyde testing. Okay? I don't have any equipment, not so many digits. Okay? So if you try doing that, you will have this answer. And in fact, from multiplying and divisions, you have to give me the least significant you can have. For example, this one is a 3-digit divided by 4 digits, 4 decimal point, 4 significant figures. 3 significant figures divided by 4 significant figures, you can only report with an answer up to 3 significant figures. And so you try to run in this digit. And so you give me this one. Clear? Okay. Points to note. Further tools. First of all, log. Okay. You also might use log in your calculations. When you do log, okay, something you have to bear in mind. Before that's for example, no, not like this. Don't be like this. For example, like this. Can anyone tell me how many significant figures for this value after an operation of log? How many significant figures for this case? If you go back to the previous slides, you probably will give me 5. 1, 2, 3, 4, 5. Right? Anyone object for this answer? Or anyone still puzzled about the decimal point, decimal significant figures? And in this case, I will tell you this answer is wrong. Why? I give you one example. Like here, you have 120.35. Okay? Now, use your calculator to compute log. Tell me what is the answer? You will have your answer of 2.010087847. Okay? Just copy from your calculator. Okay, now tell me what is this? Tell me what's the result of this one. I just move the decimal point. You probably will have Okay, so what's the answer? Okay, so from this exercise, you would know the log systems using this to store the value of your data. And this part is telling you where the decimal point is located. Because 2 is talking about 10 to the power 2, which is 100. So the first digit is 100. 1 means 10 to the power 1, which means it's equals to 10. So the first digit is at the 10th digit. And this one is at decimal point. So it's 0. If you try to guessing this one, furthermore, for example, if you tell me that it's -1.01, okay, then it will be okay, somewhere here. Okay? Something like that. So from these systems, if you now know about the log systems, you should be able to tell me that this part is for storage of the values of the data. And this one is talking about the decimal point. So this one, the point after the decimal point are significant figures. Whereas this is not significant figures. This is talking about where the decimal point should be placed. So this one is not counted as a significant figures for logarithm. And so back to the answer of this one, you only have 4 significant figures. So if you try to anti-log of this value, you can only give me the answer in 4 significant figures. Okay? Okay now? Okay? And one more thing is when you do your calculations. Okay? I understand in your calculation you might have plus or minus, you might have multiplying, you might have divisions of data, you might have square root, you might have square, a number of operations. And when you try to run the results, okay, if you every time when you do a plus, then you run once, or anytime you try to do a divisions, you run, or you try to run at the end of all your operations complete. Which one is the correct approach? From the notes, it tells you that you have to run at the end of all your operations has been done. Therefore, I would like to conclude why you guys have different answer. It's because some of you guys, when you do calculation, you running every steps. Some of the guys, when you do calculations, you do running at the end. Some of them would run randomly, okay? Because they try to write the answer on the answer book, and every time when they try to calculate the next steps, they copy from their answer book, and so it ran once. Okay? So different people would have different rounding habits, and therefore there would be many different versions of your answer. Okay? And so I would like to share with you is that someone asking me to borrow money. I would like to tell you that when I try to marking the students who taking this course in the final exam, I use it to get many different versions of the answer. So there's no defined answer for this course. It's another set of measurement and certainty. Okay? So from this lecture notes, you already learned how to do correctly for your answer. Okay? So what you're going to do is, I will have a Kahoot for you guys to practice. So, try to log in with your student ID, please. Try to log in with your student ID, please. Very good. You can identify you still remember your (1155). Why is it 1155? Oh. You see, that is uncertainty. I still remember my student ID. How many digits? My student ID got 8 digits only. Okay, and you guys still can also read from the student ID when I entered this university. Do you have ideas? The systems, previously the systems this is the year of your entry. This is which college you have enrolled to. Okay? Okay, you know this college? Okay? I study from this year. Okay, long before you birth, I think, for most of you guys. And so, with this, only 25 There are 32 people in this class. Come on. This is not a valid student ID. I use it to collect some of your IDs in order to prove you are there. Hey, come on. Show me you are human beings here. You still struggling on how to connect 30. Okay, I think I have to start. And please take your calculators to do the calculations. This exercise definitely needs calculations. Okay? Okay, so one student have this one, okay, very famous, typical wrong answer by copying your calculator, okay. This one is not correct because they don't have the units. Okay, when you do calculations, don't forget your units. This one, plenty of students take it, okay? And it's not correct because it is a 4 significant values times a 3 significant values. So the answer should be 3 significant. So the answer is this one. Okay? Very simple practice. Okay? Very simple practice. And you can still see 4 different versions of answer appear in this class. Okay? Next one, see if there's any improvement. Determine the answer with correct significance. That is very common in chemistry. That are constants. You cannot see that. Come on. Okay. So, what's wrong for this two? Obviously, these two didn't take the log. They forgot to take the log. They just do the divisions of that. And this one, This one is very typically copying the answer from his calculator. Okay? This one, because if you take back to the questions, it's just got two certain figures. Two certain figures divided by three certain figures. So you have to report two certain figures. But bear in mind, for law, this digit is not significant. So this one is correct, and this one is not correct. Okay? Okay? Clear? Clear? Understand how to pick the correct certain figures? Okay?